All right, so I wanted to talk about some things before getting back into vector spaces. A silly thing, it's called a vacuous truth. We'll only really use this in one specific case, but it's a good little set theory thing to understand since we've been talking about set theory. So a vacuous truth is a statement that's true without needing to prove anything, essentially. Like there's something about the set that I'm talking about. And if you think about the word vacuous, maybe you understand what the set is that we're talking about, that there's not much that you need to prove. So can someone say why the statement all unicorns are red is true? Just think about it. Yeah, if there are no unicorns, which I think there are no unicorns, right? Exactly, it can't be disproven. Like, how do you disprove something? Yeah, how to disprove, you need to find a unicorn that's not red. Right? Yeah, so contradiction is good. I think proof by counterexample, there always exists a counterexample, right? If you say something is true and you can find at least one counterexample, then that statement is no longer true. So if I say all unicorns are red, all you need to do for me to disprove that is to find a unicorn that's not red. But if unicorns aren't real, then you can't disprove that. So this is something just silly to say, and it's not a self-contradiction. I could also say all unicorns are not red. Yeah, that'd be another one. All pigs that can fly are yellow, right? But no pigs can fly. Yeah, unicorns are all the colors of the rainbow and at the same time not any color of the rainbow, right? Because those aren't self-contradicting, right? All unicorns are red and all unicorns are not red, right? The only case where that can't be true is if there is a unicorn, right? So yeah, so what is that? What set are we talking about? About all unicorns? What is that set called? What is the set of all unicorns? Some unicorns are rainbow. Sure, yeah, that's fine too. Well, depends on what you mean by some. If you mean some meaning there implies the existence of more than one, it depends on how you define some, I would say. So what's you mean like union? Well, yeah, but I mean like what is unicorns? The set of unicorns is what? It's empty, yeah. Well, there are no unicorns, so there's nothing to say. So vacuous truths are something about the empty set. So for example, all dragons are evil, all dragons are good. Notice that you can create contradictory statements because it's really not a contradiction because there's nothing to say about the set of all dragons, right? It could be good, evil. You don't even have to do with things that don't exist. You could say things that are just not in your set, like all lizards taking this class. Well, I don't think there are any lizards taking this class, so they could be whatever you want it to be. So, and again, how would you contradict that statement, all lizards taking this class are named Mark? You need to find a lizard in this class whose name is not Mark. So now, I guess, again, all of these things are, so vacuous truths are something about the empty set. So even specific about the empty set, every element in the empty set is a cow. Every element in the empty set is a number. So can someone say why that makes sense? Why does every element in the empty set? What is every element in the empty set? Yeah, since there's nothing in the empty set, everything in the empty set is whatever you want it to be, because you're not talking about anything. So let's try to whenever you talk about the empty set, you do need to keep in mind what is a vacuous truth and then what is not a vacuous truth. So there are some things about the empty set that are false, but some things that are these kind of obvious truths. So now let's go back to our thought about vector spaces. So here, this is what we define a vector space as. It's a set with two things. It has a binary operation and it has some scalar multiplication in a field. So what must be true about the binary operation? Let's just go through it. Let's say V, W, and Z are vectors. Let's say alpha, beta are scalars in the field. Can someone remind me what closed means? I'm saying the binary, let's call the binary operation plus. And let's call the field multiplication circle. What does it mean for the binary operation to be closed? Yes, the input and output are the same. So you can say V plus W is in V. Right, if I take the input, which is V plus W, or V and W, and the output is V plus W, I must get an element in the set. Okay, what does commutative mean? You can use VW if you want, and plus. So what does it mean for the binary operator to be commutative? That's, you're using three vectors though, but the part of what you have is true. So I'll just use it in two letters. So V plus W is equal to W plus V, right? You can flip flop the pluses. What does associative mean? So now this is the one that you might need three vectors for. It's the one with the grouping, right? This is V plus W plus Z is equal to V plus W plus Z. Can someone give a definition for identity? What's the identity element in a binary operation? Good, yeah, it's the number, or it's the vector where if you add it to another vector, it doesn't change that vector. So V plus 0 is equal to V. So 0 is the identity. What does inverse mean? Sure, yeah. So for multiplication, it would be like 1 over. For addition, it would be negative. So it's the number where if you use the binary operation on it, you get the identity element back. So now let's go through, what does it mean for, what is scalar multiplication? What does that mean? So that's all for binary operations. So now let's go for scalar multiplication. What does it mean for scalar multiplication to be closed? Well, first of all, what is scalar multiplication? You need to say that in words. or maybe can you use it, describe it as a function? I like input output. So I'll do half of it for you. It's the output is a vector, but what are you inputting? So just like binary operation, right? It's input two vectors, output a vector. What does scalar multiplication mean? Scalar in a vector, yeah. So you might say, so the scalar is the element in the field, and then maybe V is the vector. So the two inputs are a scalar and a vector. And when I say closed, it's an element of V. So this alpha, so the circle just means the function. So that's an element in V. So how about it's distributive? So what does distributive in vectors mean? So yeah, what does that mean? What does distributive mean? So we know what distributive means, right? But for the first statement here, distributive in vectors, what do you think that would mean? So use maybe alpha for the scalar. So the vector binary operation is V plus W. Good. So this will equal alpha V plus alpha W. And distributive in scalars is the other way around, right? It's if you have a sum of scalars times a vector, it's alpha V plus beta V. Now, does anyone remember, of course, all these are circle, right? You remember compatible? What does it mean for the multiplication to be compatible with field multiplication? Because these are different multiplications, right? Field multiplication is multiplying two scalars, but scalar multiplication is a scalar times a vector. Yeah, it's the one that kind of looks like associative, but we don't call it associative because there are different operations going on. So it's the one that looks associative though. So it's alpha composed with beta of V. So this is all scalar multiplication. And it kind of looks like associative insofar as you can group the scalars apart. So the idea is that this is field multiplication. And this is scalar multiplication. Yeah, these are equal. So it looks a lot like associative, but the idea is that there's different multiplications going on. And then what is identity preserving? So what I mean is if I do the scalar 1 times V, what do I get back? V. All right, so when we're going to prove that things are vector spaces, and we have to prove everything, all of these axioms. But notice a lot of them are not that bad, right? It's commutative, associative, distributive. This one might be kind of weird to think about, the compatible. There would be some cases where that you actually do have to care about that, but I wouldn't say that none of them are like overly complicated, but it is a lot to go over. But I like to kind of break it down into binary op and scalar multiplication, because other ways of describing axioms as a vector space is just, here are 8 axioms, and I think 8 is a lot more intimidating than 2 times 4, personally. But so I recommend kind of splitting it up like this, just like the binary op operation first and then do the scalar multiplication. Okay, so with all that, let's start figuring out if things are vector spaces. So is the empty set a vector space? So do you think it would matter what binary operation we choose? And do you think it matter what field multiplication we choose? Let's look at the, yeah, it wouldn't really matter, right? Any binary op, any field, scalar op, mult with any field. Right, because is it closed? Can you say why it's closed? Why would it be closed under any binary operation? Yeah, there's nothing to do, right? So it's vacuously true, right? The sum of any two elements in the empty set is an element of the empty set. Well, yeah, there's nothing to do. So that's true. But let's go through scalar multiplication, because there is one thing in the binary operation that is not true about the empty set. So closed, we talked about that, yeah. If you take any element in a field and multiply it by an element in the empty set, since there's nothing to multiply, there's nothing to do. Same with compatible, that's fine, right? Since there's nothing to choose for V, right? Like for all V, this needs to be true, but since there's nothing to check, it's vacuously true, right? Like for all, so this is like compatible. For all V in V, and all alpha beta in F, then ... The idea is that when you say for all V in V, so for all V in the empty set, no matter what you say after that has to be true, right? Because there's nothing to counter it. Does that make sense? Why compatible makes sense? There's nothing to do. So really everything on the scalar side is fine, right? There's no vector to choose. Okay, yeah. It's inverse isn't the problem though. It's what does inverse mean? What do you need to have an inverse? Inverse only makes sense if you have something else, right? What is the word you need? You can't have inverse without this. Identity, yeah. Right, so before inverses, you have to have identity. Does the empty set have an identity element? So, and the answer is no, right? Identity means there has to be an element in the set where if you add that to any other element, it doesn't change. But the third axiom says there needs to be an element called identity. There needs to be an element called identity. Right? But the empty set has no elements. But the empty set has no elements. Right? So it's not vacuously true because, right, this would not be a true statement. The empty set has an element in the set, right? Because the empty set has no elements. Multiplying a set with the empty set, well, you need to define like what multiplication of sets means, right? Then that might be a union, which would not be the case. But just with the empty set itself, it fails vector space because you need an element. So does that make sense why the empty set is not a vector space? The identity axiom is very important. You need something in there, right? Called the identity element. So there has to at least exist something called the identity. So given that, what do you think? So if the empty set is not the most boring vector space because it's not a vector space, what do you think is the most boring vector space? Yeah, the most boring. That's not a mathematical term, boring. Most boring vector space is 0. So, and why is that a vector space? So, I should have, I was going to copy and paste these things. Yeah, why is that a vector space? Well, let's kind of give some binary operations and scalar. Yeah, so if I, let's just say usual addition, matrix addition, and let's just do normal scalar multiplication. Meaning like if I have alpha times v, it's just alpha v like we normally think of multiplication. Yes, everything will be 0. So does it work for closed? Actually, I'm going to copy and paste this. So does it work for closed? So if you take any pair of elements in 0, is it in the set? Yes. 0 plus 0 is equal to 0. Good. Is it commutative? Well, yeah, these are commutative. It's just our normal addition. What's the identity element? 0. Yeah. 0 plus 0 is equal to 0. Good. And what's the inverse of 0? 0. 0 plus 0 is equal to 0. Saying the same thing 3 times for each one. Now let's do scalar multiplication. If I do a number times 0, what do I get? 0. So I do a number times the sum of vectors, what do I get? 0. I do a sum of numbers times 0, I get 0. And if I do alpha times 0 or whatever, beta times 0 is equal to alpha beta times 0, yes, all these are 0. And 1 times 0 is 0. So yeah, so this is the most boring vector space. It's just one element. Okay, can we go maybe one up from that? Can we do this? Is that a vector space? Let's do normal plus and normal scalar mult. Is that a vector space? Let's think about it. Let's go through, bring it over here. So why do you think it's a vector space? So remember for the addition, they don't have to be different. They don't have to be different elements. They could be the same elements. But what pair of elements when you add them? Yeah, 1 plus 1. 1 plus 1 is equal to 2, which is not in 0, 1. It turns out when you just add a little bit more, it's not a vector space. Yeah, so when I say V plus W, I'm not saying that V is not equal to W. It could, but in particular 1 plus 1. And also, it wouldn't have an inverse too, right? Negative 1 would be the inverse of 1. But that's not in the space. All right. So you imagine, so vector space is probably going to be kind of big, right? Correct. So for this to be called a vector space, it needs to satisfy every single one of these, single one of these properties. If it fails just one of them, then it's no longer a vector space. All right, so let's do some examples. Let's do polynomials. So we're going to call polynomial addition by adding like terms. So for example, if I have, okay, first of all, does this make sense as a polynomial? Yeah, so we'll call this P of X. And what we're going to call addition let's use a different letter, M. They don't have to be the same degree. Let's call this Q of X. What we call polynomial addition is just adding like terms. So you group all of the constants together. You group all the first power terms together. And you group all of the nth power terms. And what if they're different degrees? What do you do? Let's say m is bigger than n. What do you do next? There's no n plus 1 power, right, in P. So you just do, so there's nothing to add in the P of X term, then you just don't include that. So is that a polynomial that I just wrote? If this power defining addition? So this is what we're going to call P plus Q of X. Is this a polynomial? Yes. So it's closed, right? This is a polynomial. So it's closed. Is it associative or is it commutative? If I did Q plus P, would I get the same thing? Like, would this be the same? Yeah. And why is because when I do the like term expression, it's just normal numbers, right? So AI plus BI is equal to BI plus AI. So associative also true, right? And again, it's because the coefficients are AI plus BI plus CI, and depends on what order you multiplied. So we won't do all of them. But can you tell me the identity element? What's the identity polynomial? So what polynomial do you add that doesn't change a given polynomial? Yeah, 0 is a polynomial. Yeah, 0, right? It's just 0 plus 0x plus 0x squared, right? That's still a polynomial. And yeah, inverses are just negative px is just what do you think negative px would be? What's the negative of a polynomial? Negative? Don't think too much about it. It's if you have a polynomial, what do you add to it to get 0? What do the coefficients look like? Yeah, everything's just negated. Yeah, so negative a0 minus a1x minus a2x squared minus blah, blah, blah. All right, so how about you do scalar multiplication? But it is a vector space. So it's kind of, it's easier to prove, but let me ask you this. How about polynomials with multiplication? So, I mean, P of X times Q of X. Does this satisfy all the axioms? So let's bring back our axioms. So the binary operation is now multiplication. So let's talk it out, and we don't have to prove everything because it turns out it's not a vector space. Let's talk it out. Is it closed? Is the product of two polynomials a polynomial? Yes, right? When you do the foiling, right, it's gonna be a lot of foiling, you're always gonna get powers of X, right? You're not gonna get any other thing. Commutative, yeah, it's multiplication. Associative, yeah. What's the identity for polynomials? What is the polynomial that you multiply by to get the same polynomial back? 1. Yeah, that is a polynomial, right? It's 1 plus 0x plus 0x squared, right? That's a polynomial. How about inverse? What's the inverse of a polynomial? Yeah, is that a polynomial? So I have P of X inverse, which is, yeah, probably 1 over P of X, right? Because P of X times 1 over P of X does give you the identity back. But is that a polynomial? So what does polynomial mean? Polynomial means you have these coefficients with powers of x, with positive powers of x. Yeah, polynomials don't have negative powers. No polynomial has negative power. Yeah, so you can't divide polynomials. So one easy one, even if you include like negative powers, even if you want that to be included in your set of polynomials, like how about this even? All right, you can't express that as not as a finite polynomial. Maybe if you've taken Calc 2, you know how to express that as an infinite polynomial, but not as a finite polynomial. So the binary operation really matters in these things, right? So polynomials with addition is fine as a vector space, but not as multiplication. Okay, let's do another one. This is a fun one. Okay, let's do lines. Okay, let's let our set be a set of points on the plane, x, y, and let's have all the y values be 2x. And let's have the binary operation be addition, where xy plus vw is what we like, is x plus v and y plus w. And let's let scalar multiplication be alpha xy is equal to alpha x, alpha y. So it's vectors just of this form, where the y value is twice the x value. All right, so let's get our list out. And let's see if this is a vector space. So now things are a little more interesting, right? How do you show it's closed? Someone tell me, like, how would you just determine if it's closed? What would you need to check? All right, what does closed mean? You say the words, then it's kind of easier to check. What is that? What does closed mean? Okay, x 2x, but that would be an example. That would be things in the set, yeah. But what does closed mean? It is still in the set. What is it? Sure, the elements, but say exactly the words, right? The result of the binary operation, right? So how do you say that in words, in math words? It's this, right? You want to say that this is in the set. So let's like say exactly that. So x 2x is in the set, right? Can you give me another random example of something in the set? Don't give an actual number, but good. Not 2w, but 2v, yeah. Plus v, 2v. What is this equal to? Based on our definition of addition, what is this equal to? Good, yeah, x plus v and 2x plus 2v. All right, so now what does it mean for it to be in the set? The definition of the set is that the y value is twice the x value. Is the y value twice the x value here? And by x value, I mean first coordinate, and by y value, I mean second coordinate. Is the second coordinate twice the first coordinate? Yes, and how can you show that explicitly? Factor out the 2, yeah. So this is exactly how you would go about proving closed, is that you give two variable expressions for something in the set. So x2x and not like 2, 4, but v, 2v. You add them up, and then you express the result as an element in the set. All right. We'll ignore commutative and associative because we know about matrix addition. What's the identity element? So what vector do you add such that nothing changes? So look at the just 0. So yes, the 0 vector, but how do you say that in the vector? Yeah, 0, 0. So x, y plus 0, 0 is exactly x, y. Good. Oh, but yeah, it is 0, 0 in the set. So not only does there need to exist an identity element, but the identity element needs to be in the set. Yeah, is 0x, 0y an element in the set? Well, what is the definition of it being in the set? Is the y value is twice the x value, right? Is that true about 0, 0? Yeah. 0, 2, 0, not 20. 2 times 0 is equal to 0, 0. And inverse. Sorry, we didn't get through a lot today, but so if I have x, 2x, what do you add to it to get to 0, 0? Or how about negative 2x? Yeah. And is that in the set? So negative x, you might want to express it as 2 times negative x. Right, so that's in the set. All right, so I think I spent too much time on the midterm, but so Wednesday we'll finish up vector spaces. But I think you have a good idea of at least checking for the axioms. But Wednesday we'll do some ones with weirder binary operations and some weirder scalar multiplication. And we'll look exactly at what how vectors behave specifically on a plane. So that will be next time. Yeah, so that happens sometimes, it lags. But I'll stop recording.